So, good evening, everyone. I'm here to present to you a journey in which several players have been involved. And this journey is about a project which has been helped by and funded by European Union, Innovate UK, and Swiss Confederation. The project is called NeuroSoC, and okay, I will not repeat the title because it was too long the first time. And our summary, it will be about presenting you a little bit about this project, what we are doing. We will present to you the NeuroSoC architecture, the enhancement that we are working on the architecture with the RISC-V support, and the architecture of the RISC-V core, plus the RISC-V core processor unit, the emulation platforms that we're using, and the future works, of course. These are all the players involved in the project, which started in the end of 2022. So it's a 42-month project, and it will end in the beginning of 2026. As you can see, there are lots of companies and lots of universities involved here. So what is our background here? We know that in a lot of artificial intelligence applications, we have the issue about developing all the calculations in software, so we need some hardware to accompany it. And to do that, we do that because we want edge-end devices and edge-end applications. Plus, we want this because we want to develop some kind of applications that are power savings and energy efficient. The issue here is that in a lot of cases, if we want to use a conventional, let's say, von Neumann application, it's that we are usually encountering several issues among the bandwidth, the energy, the throughputs that the architecture can support. That's why we recurred to some kind of new paradigm, which is in-memory compute, using phase-changing memories. And this is the answer that NeuroSoC is trying to give this kind of issues. We want to develop a flexible computing system where an analog IMC-based neural processing unit is integrated into a multiprocessor, functional, safe, and secure system on chip. We want to have a solid, mature, and qualified, reliable phase-change memory that we are using inside the project. And we want to tackle these kind of issues that we saw to achieve the creation of an industrial proven path, answering the level of maturity needed for compatible with a mass volume production and costs. So this is a block scheme of what we are doing right now. As you can see, we have a mesh structure on the left. And in this mesh structure, not all the blocks are the same. So we got a lot of analog in-memory compute blocks which are developing the usual convolutional operations, which means multiply and accumulators. And we also have got RISC-V blocks, load and store units, and digital processing units. Like all these kind of blocks are, of course, different in the operation that they are developing. For example, we developed the convolutions inside the AIMC, but we use the digital processing units, for example, for the thresholds or for depooling or for other operations needed inside the neural networks applications. What we are doing, which is kind of the same for all the blocks inside, for all the nodes inside the mesh, is the control that you can see here. And then you got the border guards. The border guards are the main part of this kind of architecture because they are interfaces to the outside for the nodes. And with this kind of border guards, which are synchronized and which the information comes from the RISC-V, we are able to make all the paths inside the mesh working correctly. What we don't want here is to have loops inside a path, inside the mesh between the nodes. And plus, we want the controls to be able to exploit these RISC-V operations and instructions. As you can see, you could have seen it also in the slide before. Here it is highlighted. We got two RISC-V structures inside. One, it is a coprocessor that will provide a programmable inference accelerator directly embedded in the MPU cluster. and one other is an host multicore component that will provide a RISC-V multicore enhanced with functionality safety features. So what we are trying to say is that the first one on the left will give us the instructions and the operations that all the other nodes in the mesh needs to perform, while the RISC-V functional safe on the right will give us a check, a control, some redundancy to check if all the operations in the end are done correctly. And we are starting from this latter one, which is based on a CVA6, and which is an open source RISC-V application core able to boot Linux, and it's curated by OpenAir Hardware Group. In this kind of application, we have two different flavors, let's say. One is on 32 and one is on 64 bits, which are CVA6 and CVA64A6. And we got some other features, which are a dual core configured, or DCLS, which are needed for redundancy. And then we got an internal memory hardening, which has an error correction, also to check if everything went well inside the calculations in the mesh. The other unit, which is based on RISC-V, it's the core processor unit. And in this one, we use several modules that can be combined, which are called niche processors, which kind of gives us the inputs, the operations, and the instructions that are needed to be fetched and given to the other meshes, to the other nodes in the mesh. These all are connected to a scratchpad memory, a cache here, and it also has got some hardware processing elements which tends to solve us the issue in which we will have to develop some floating point operations. The operations inside the mesh in the nodes regarding the AIMC are developed principally in fixed point and in integer. So if we need some floating point extension, this issue is solved here by the hardware processing unit. And then, of course, we got the DMA for efficient data mover, and we got the IMNPU mesh, which is a sort of interface to interact with the nodes inside the mesh. So we developed two emulation platforms regarding this kind of this project. And the first version is an emulator which is based on Xilinx Kyria boards. This emulation platform can provide a lot of flexibility because, of course, we have the possibility to scale. We have a huge scalability because we can just add more Kyria boards to provide more processing units, processing elements, and which utilize TCP/IP protocol. Plus, there are a lot of functions which are built in for debug and time-stamping mechanism. This kind of solution is, of course, good in a first phase, because, of course, in a first phase, we want to have a huge amount of debug, let's say, and applications that can check what we are doing to develop it faster. But in a second stage, it's kind of limiting in some cases. So we also went for another emulation platform. This other emulation platform is based on boards which are Alveo U50. These kind of boards are a lot more powerful than ones we saw before. And this version will have similar functionality as the one previously described, but there are some differences. Let's see what the differences are. So principally, the Alveo U50 offers 8 times more resources than the Kyria, which means you can instantiate more processing elements inside one single board. Second, the PCIe Generation 3 with 16 lanes offers up to 120 gigabit per second transfer rate for the fast data transfers. And we are also, thanks to that, achieving higher data transfers. What we do not have here that we had before. With Kyria, you can, let's say, extend your processing elements, and you can have more processing elements simply by adding more boards. In this case, you can't. While the second stuff is that the functionalities provided by CREA about the debugging and the checks are not provided here. So you need to do that, let's say, outside. So what are the future works and how are we moving right now? So first of all, the design and architecture has been completed and the porting of the emulator is ongoing right now. The next step will be to validate the prototypes in terms of quality of detection, efficiency, and security enhancement. There are also a lot of other stuff that are ongoing right now, which are principally regarding the developments of new features inside the mesh and inside the nodes, or other processing units and processing elements inside the digital processing units. Because, of course, we will need to check if other functionalities are available and can be ported inside. This project, as I told you before, is it will end in the beginning of 2026, so we'll have a little bit of time left. But right now, everything is moving forward, and this is a huge step forward for us and for the people working for us. And pretty much that's it. Thanks for attention, and if you have any questions, I would be happy to answer them.
Hi. Is any of the work open source, publicly available now?
Not yet. It's something that's it is a European project funded project, so some of the results will be published in the end of the project or in the final stages. We have some publications on that, but like it's not totally open source, of course.
Sorry. Can you please elaborate a little bit more about functional safety and RISC-V?
Okay.
Slide 7. You mentioned Linux, and I think it should be some different operating system. Am I right?
Okay. So if we go back to the slides for the I don't know if we can have them, but we got some structures inside our RISC-V, which are dual locks. Okay, thank you. Okay, so yeah, we got a dual core configured as AMP and DCLS. DCLS are usually used for redundancy checks. And so this is kind of a functional check here. And then we go for internal memory hardening with error correction. Because this kind of unit, RISC-V unit, is used in the end of our calculations to check if everything we've done has been correctly done. So this is kind of the function of the host RISC-V processor. And this is based on an open source one. I don't know if I answered your question. Thank you.
Thanks a lot, Carmine. Great presentation.
Thank you.